In the last few lectures, we have introduced to the area of quantum information, and in particular we talked about concepts like Shannon entropy and its quantum extension, namely von Neumann entropy. We wish to end this series of lectures with a discussion on quantum cryptography, but before we do that, a question naturally arises: how reliable is quantum mechanics? How robust is the information sent using the processes of quantum mechanics over a quantum channel or over a public channel? In order to do that, we would need to establish the supremacy of quantum mechanics over its classical counterpart. I have pointed out several times that right from the beginning, even distinguished people such as Einstein did not believe what is known as the Copenhagen interpretation of quantum mechanics. Today we will discuss what is this objection that Einstein and his co-workers had, which goes by the name of Einstein-Podolsky-Rosen paradox, or in short EPR paradox. Firstly, let's talk about what we have been saying as the entangled state. Now, what is meant actually by entangled state? I have given you several examples. Take the example of one of the EPR pairs, these Bell states. These are 2 qubit states given by, for instance, one of them is 1 over square root of 2, that's a normalization factor, into 0, 0 plus 1, 1 state. And this is a maximally entangled state. What I mean by a maximally entangled state is this: supposing I am to take a reduced trace over either of the qubits, then the result that I would get would be not a pure state, but a mixed state with maximum mixedness. That means the density matrix rho turns out to be equal to half. The beautiful thing about entangled state, beautiful or curious thing about the entangled states is that if you made a measurement on one of the qubits, the second qubit automatically gets fixed, and the information that could be there in the entangled state otherwise gets lost. So the idea is this, that a measurement of the first qubit would collapse the second qubit as well. Now, what was Einstein's objection to this whole thing? What Einstein said is this, that supposing there are 2 objects, in this case my qubit number 1 and the qubit number 2 of the Bell pair, they are separated by a space-like distance. What is meant by a space-like distance? It means a distance which cannot be even traveled by time. Well, in practice what it means is that supposing you are making a measurement on one and you are making a measurement on the second one, during the time that it takes for the light to travel from one qubit to the other, any measurement made within this time interval cannot have influence of one measurement over the other. But however, according to the dictates of quantum mechanics, the moment you make a measurement of qubit number 1, the qubit number 2 gets fixed. So in other words, despite Einstein's objection, the second qubit did collapse as a result of the first qubit measurement. So in 1935, Einstein, Podolsky and Rosen, this paper is a very well celebrated, often talked about paper. This is known as EPR paradox. They questioned the Copenhagen's interpretation of quantum mechanics, and it led to a phrase called spooky action at a distance, this correlation between the 2 particles, irrespective of how widely they are separated. Einstein thought of a thought experiment, and which points towards what Einstein called as the incomplete description provided by quantum mechanics. Because according to Einstein, a system must have what he called as an element of physical reality. So let me explain in Einstein's words what physical reality actually means. To quote Einstein, if without in any way disturbing the system, we can predict with certainty, by certainty he meant with probability of 1, the value of any physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Now, how is it different from what the quantum mechanics says? Remember, quantum mechanics says the value of a physical observable has no meaning independent of its measurement. So, in other words, its value gets fixed the instant we have made a measurement. But Einstein thinks that you got that result because that was the value that was somehow or other encoded in the system. So let us look at a little more about Einstein's objection. Supposing we have a combined system which consists of two systems and they had interacted during a time interval from t equal to 0 to t equal to capital T. And after that they got separated and they did not interact. Now this combined state of the system, this is known from quantum mechanics, and their development is decided by quantum mechanical laws, namely the Schrodinger equation, even for time t greater than t, capital T, when they are no longer interacting. Now the problem is this, that we cannot calculate the state in which either subsystem was left after the interaction without the measurement, that is by collapse of the wave function. Now let us look at a simple example. I could give some more, but this example is, consider a particle at rest which disintegrates into two equal mass particles. We have learned that if the particle was at rest, its momentum was equal to 0. So therefore, since the disintegration process is an internal process, this will conserve momentum. In other words, after the system of one particle has disintegrated into two, the momentum of the pair will continue to be 0. Now let us look at what happens. Now Einstein's objection would prove I can fix simultaneously the position and the momentum of one of these particles, either of these particles, in spite of the objections that is posed in quantum mechanics due to what is known as Heisenberg's uncertainty principle. In this particular case, let's consider, suppose the two particles disintegrated and moved away from each other along the x direction. Now if you are looking at one of the particles, let's call it particle number 1, then according to Heisenberg's uncertainty principle, I cannot fix the position of the particle as well as its momentum. That is, I cannot talk about simultaneously about its position and momentum at a given time. Now let's see whether that would be correct or not. Einstein's objection would be the following, that suppose you made a measurement of the momentum of particle number 1 and position of the particle number 2. Now this is possible because Heisenberg uncertainty principle doesn't raise any restriction on different measurements being made on the same particle at the same time. But however, since the momentum is conserved, a measurement of the momentum of particle number 2 will fix the momentum of particle number 1 as well. So if the momentum of particle number 2 was P2, the momentum of particle number 1 will be minus P2 because the net momentum was equal to 0. Similarly, if at the same instant I measured the position of particle number 1, because of the fact that the center of mass must remain fixed, I would be able to calculate the position of the particle number 2 as well. So in other words, at the same instant I have information regarding both the position and the momentum of the particle, and that is something which was Einstein's primary objection to the Copenhagen interpretation of quantum mechanics. I could give other examples, but let us look at the following thing. So, what is meant by local realism? So, realism according to Einstein's interpretation means an object possesses property independent of the measurement, and this property gets revealed only when a measurement is made. In other words, measurement is not the process which gave the attribute to the particle. The measurement simply is a revealing process. Secondly, the Einstein's another phrase is locality. Now, what is meant by locality? Locality says a measurement on one of the members of the combined system, in this case one of the members of the entangled pair, cannot influence the property of the other member. That is a locality, because a measurement that you make in one place cannot influence the property of another particle in another place. Well, in particular, if they are separated by a distance such that the property measurement that I am making on the second particle is shorter than the time that the light takes to travel from the instant the particle number 1's measurement was made to the particle number 2. So, this is locality. So, Einstein demands that a physical theory, in order that it is understandable, must have local realism. This has two components. One is locality, that is independent of what happens to particle number 1, the particle number 2 possesses certain property. And realism, that is, it is not the process of measurement which gives the property to a particle, but measurement simply reveals what was already coded in the particle. This was known as, probably Einstein did not use that word, but this is what is indicative of. Probably Einstein thought that there are some hidden variables in the problem which encodes the property of the system. To understand it in the language of quantum mechanics, let us look at a slightly different version of the same EPR paradox, and that is due to David Bohm. In 1951, he presented a version of EPR paradox using a composite system which has a spin 0, and this system decays into 2 spin-half particles. Now, this is routine because you will find enough examples in nuclear physics and particle physics where a spin 0 particle decays into 2 spin-half particles. So, we know again, because the angular momentum is conserved and I had started with a spin 0 particle, the net angular momentum of the 2 particles into which the combined particle has disintegrated should also be in S is equal to 0 state, which means that the particle will be in this state. So, let me write down up down minus down up in the language in which we are familiar in quantum mechanics. So, what it means is that the Sz value of particle number 1 is up spin, you could call it Sz equal to h cross by 2. The Sz value of the particle number 2 is a down spin. So, up down minus down up. Now, supposing this qubit, 2-qubit system, gets separated by a distance such that disturbance on one cannot have an influence on the second one. And let us assume that the particle number 1 is held by Alice and Bob holds the particle number 2. Now, suppose Alice now makes a measurement of her spin, her qubit, what is the SZ value. And suppose Alice's measurement says that the SZ value of particle number 1 happens to be in h cross by 2. That is, we will say sigma z, that is the value of the Pauli matrix, eigenvalue is equal to +1. Now what we are saying here is this, that according to Bob, if he now measures the particle that he has, he is guaranteed to get. So Bob's measurement will definitely give him SZ equal to minus h cross by 2, meaning thereby sigma z is equal to -1. So you notice that what we are talking about here is this, that Alice's measurement and Bob's measurement have a perfect anti-correlation. If Alice gets up, Bob gets down. If Alice gets down, Bob gets up. Now suppose Alice still made the measurement and got a spin up, but Bob decides to make a measurement in an arbitrary direction. So suppose Bob's measurement direction is n, which is equal to x component sin theta cos phi, y component sin theta sin phi, and of course cos theta. Now what happens to Bob's measurement in this case? Remember, Alice has got SZ equal to +1, and Bob is now not measuring along the z axis, but is measuring along the arbitrary axis, which makes an angle theta with the z axis. Now let us recall that along an arbitrary direction, we had talked about it long back when we had just started introducing the qubit and its block sphere representation. We said that if you look at sigma n, that is the component of the Pauli matrix, along an arbitrary direction, then the eigenstate of the Pauli matrix corresponding to the eigenvalue +1 is given by cos theta by 2 e to the power I phi sin theta by 2. In fact, you could write it more symmetrically by pulling out a factor of e to the power I phi by 2 and write it as cos theta by 2 e to the power minus I phi by 2 and sin theta by 2 e to the power plus I phi by 2. And correspondingly, the eigenstate corresponding to Sn equal to -1 or sigma n is equal to -1 is given by same e to the power I phi by 2. This normalization factor I will ignore in subsequent discussion. I get sin theta by 2 e to the power minus I phi by 2 minus cos theta by 2 e to the power plus I phi by 2. Remember that eigenstates belonging to different eigenvalues must be orthogonal to each other, and hence one of them has a minus sign, and these eigenstates are properly normalized. So now let us look at what are the rival points of view that is there. So according to quantum mechanics, a particle does not have property independent of the observation, while and the process of measurement in quantum mechanics at best reveals a result based on certain probability. Hidden variable says the property of the system is simply revealed at the time of measurement, but was preordained. Maybe it was encoded in something that we cannot look at. It is hidden from our both understanding and our eyes, and hence certain variables which are there in the system, they are known as hidden variables. Now enter John Bell. John Bell suggested a Gedanken experiment. The experiment, Gedanken experiment means these are thought experiments, that supposing one could do such an experiment, then what would one find? So what Bell did, we are going to be discussing a set of inequalities generally known as the Bell's inequalities. We will not be discussing Bell's original form, but there are many subsequent simplified versions which are essentially equivalent, and we will be talking about some of them, but we will be clubbing all of them together under a common name called Bell's inequalities. So let us look at this. Remember, we had 4 Bell states. I could start with any one of them. So let me start with the Bell state, which is psi minus, which is equal to 1 over square root of 2, 0, 1, minus 1. Now, one of the things which I can verify with this very trivially is that if you take any component of the spin for the particle number 1, I will indicate for convenience instead of numbers, because these numbers are also there, I will always refer to particle number 1 by A, because it is a qubit belonging to Alice, and the second one I will call it as B, because that is a particle which belongs to Bob. So that is second number particle. Now I claim that if you take ith component of sigma, sigma first particles and second particle, then when it acts on this state psi minus, that gives me 0. This is an important relationship. I will simply illustrate this with by calculating the, let us say I is equal to x. If I is equal to x, I have sigma xa plus sigma xb acting on this state. There is a 1 over square root of 2 which remains as it is, 0, 1, minus 1, 0. Remember sigma x, what it does is to make a 0 into 1 and 1 into 0. So first, when sigma x operates on these two states, I get 1, 1, because sigma x only acts on particle number 1, minus 0, 0. And then when sigma x of b, which acts only on particle number 2, I get 0, 0, minus 1, 1, because this 0 becomes 1, and you can see immediately this is 0. Just to convince you that this is not a fluke, let us look at sigma za plus sigma zb. Again 1 over square root of 2 is there, and 0, 1, minus 1, 0. Remember what sigma z does. Sigma z acting on state 0 does not do anything to it. So therefore, sigma za acting on the first state here will keep it as 0, 1. But however, acting on the second state, this 1 would become a minus 1. So therefore, I would get plus 1, 0. Simply changes the phase if it acts on qubit 1. Then I have a plus, sigma z is acting on b, so 0 is undisturbed. This 1 becomes a minus 1, and hence this minus sign. Minus 1 and 0, nothing happens by a z, and once again you can see that the terms cancel out and I am left with 0. Now this is an important result to get, because it tells me that there is a quantity which is sigma ia plus sigma ib, which gives me 0. So let us look at what does it actually mean. This Gedanken experiment that I am talking about, we will be calculating the expectation value of this quantity. Sigma A, supposing Alice makes a measurement of her spin along some direction A. So, sigma A dot unit vector A, and Bob measures along B. So, we can easily calculate how much does it give me, and one thing we have just now said is that Bob's measurement of sigma B of the particle number 2, because of the fact we have proved that sigma IA plus sigma IB is equal to 0. So, if Bob is to reveal the measurement to Alice, then Alice can conclude what would have happened if she had made the measurement in spite of her not having made the measurement. We will continue with this point in the following lecture.